Welcome back. So why do we use water as the working fluid for a Rankine power plant? Well, because right now, and I've mentioned this a couple of times already, so hopefully you already got this, that water is abundant, safe, and free. And the free is for now, because as we'll see in the example we're going to cover in the next couple of segments, we're going to use quite a bit of water for these Rankine power plants, and we typically prefer fresh water. So for all those countries that are landlocked, there's a lot of competition between fresh water that's used for agricultural purposes, for society, and for power plants. Salt water, while abundant, is typically obviously located on the shores, but in addition to that, salt water is very difficult to work with in terms of its durability on the components that we use. And we don't want salt to precipitate in our components and cause problems with the hardware and with the length of time between having to take the power plant offline and things like that. So fresh water is preferred. It's abundant, it's safe, and it's free. The next type of power plants we're going to cover are going to use air, which is also abundant, safe, and free, but it's going to take us a little while before we get to those examples. So for now, let's consider our steam power plants. Okay, this is going to take us a while to get through, but we're going to use all of our tools. We're going to consider a steam power plant that uses one stage of reheat. We're going to have a steam generator. Remember, that means it's a boiler plus a steam heater, and it's going to operate at 100 bar. The condenser will operate at 1 bar. The reheater is going to have an inlet pressure of 25 bar. If we assume there are no losses in the system, so we're going to treat this as an ideal system, we're going to consider the inlet temperature at the first stage of the turbine is 600 degrees Celsius, and the inlet at the second stage is also 600 degrees Celsius. So that's the second stage of the turbine. So for this analysis, ultimately what we want to determine is what is the cycle efficiency of the power plant. But it's going to take us a lot of work before we can get to that calculation. So we're going to do this step by step. Our first step is to make sure that we understand what the system looks like just on a sketch on a temperature entropy diagram. To do that, at the same time, we're going to draw our schematic that shows all the components and label the states. So we can map the states to the TS diagram and vice versa. Okay, for each time we ask for state information, I want you to pause as you play back this video, and I want you to see if you can answer each question before you continue. This is a great test of your thermodynamic skills that we're trying to develop. Okay, so there's our given statement. Let's get started. So we want to sketch the cycle on a temperature entropy diagram and draw the schematic at the same time. So let's get that done. Here's temperature entropy. And remember, this is a Rankine cycle, so we're going to have the vapor dome or the saturation region, and this is going to be contrary to our air power cycle, which we're going to see later. Okay, so again, we're going to draw our basic components of our Rankine power cycle. We have our pump. We're told we have a steam generator, and we're not going to break this into two heat exchangers. We're just going to model it as one continuous heat exchanger. So here's my steam generator. We're going to enter the turbine, and we're told specifically that we have 2 stages of turbine. So the first stage, we're given information, and then the steam goes into a reheater, which is modeled as a heat exchanger. And again, I'm going to show these in series, even though the turbine stages will be on the same shaft. The heat exchangers will share common features as well. But this allows it to be a little easier for us to analyze. So here's the second stage of the turbine. So I'm going to call this T1. So there's the first stage of the turbine. There's the second stage, T2. And here's my reheater. And we leave the second stage of the turbine. We go through our condenser. And then that completes our cycle. Okay. We always like to start with the entrance of the first stage of the turbine as state 1. So there's state 1, state 2, state 3, state 4, state 5, and state 6. Okay, so here's my temperature entropy diagram. I have my saturation region. And remember, my hint to you for how to draw this cycle on the temperature entropy diagram is to first determine how many isobars or how many constant pressure lines you need. And because we're considering this system as being no losses or ideal, that means every heat exchanger is isobaric. So we go and look closely at our heat exchangers and the number of heat exchangers, and that's going to tell us how many isobars we have. But we need to be a little bit more thoughtful than just count the heat exchangers. But let's start there. We have the steam generator, so that's one heat exchanger and one isobar. And because this is the high energy condition that goes into the turbine, this is the high pressure line in our system. Then we have the reheater, which is another, again, heat exchanger here. And we look and see, well, clearly there has to be a pressure decrease across the turbine because we're extracting energy from the turbine. So we know that there's a pressure at state 2 here, P2. And then at P3, we know that these two pressures are equal, right? So from 2 to 3, because we're, again, no losses in the system, this is an isobar, and this process occurs along the isobar. This is heat addition at constant pressure. And then we decrease in pressure as we extract more energy out of the second stage of the turbine, and that takes us to the inlet of the condenser. And again, the condenser is a heat exchanger, so it's an isobaric process when there are no losses. So we look at this system and we can see that there are 3 isobars: high, medium, and low. So we come over to our temperature entropy diagram and we draw those isobars. So high, medium, and low. Okay, now let's go ahead and label the energy transfers on our system schematic. Again, we have heat transfer in, we have heat transfer 1. This is the first heat addition that we have in the cycle, so that occurs at the steam generator. We generate work out, and this is at the first stage of the turbine, and then we add heat again at the reheater. So there's Q in, and I'll label that 2 because that's the second time we add heat. And then at the second stage of the turbine, we extract work out of the turbine again. At the condenser, we have heat out. And then at the pump, we have to add work in order to increase the energy of the fluid to the high pressure condition. So this is the work in at the pump. Okay, so just reiterate, we have 2 heat transfers in, we have 2 work transfers out, and that's because we have a single stage of reheat. Okay, so we've got all this information with the energy transfers. We'll come back to our diagram for the temperature entropy, and let's start with, again, the high energy state is state 1 at the entrance of the turbine. And again, if the turbine is ideal, remember we call that an isentropic expansion process as we expand and draw work out of the turbine from state 1 to state 2. Okay, from state 2 to state 3, we have constant pressure heat addition because this is a heat exchanger. And we're told the reheater has an inlet pressure of 25 bar and that the inlet temperature of the first stage of the turbine is 600 degrees C. So we could go over here and we could label this 600 degrees C. And we're told that the inlet of the second stage is also 600 degrees C. So we're going to look at this isobar. We're going to follow the isobar up until the temperature reaches 600 degrees C, and that's the exit condition for the reheater. Okay, so we want these to all be on the same line. Okay, from 3 to 4, again, we're going to expand through the turbine. And this may or may not be to the same temperature here. We don't know that. Okay, so maybe I should emphasize that this is at a slightly different condition than the other exit stage of the turbine. And then we're going to condense and draw heat out of the system until we reach a fully saturated liquid. So remember, we always like to define the exit condition of the condenser as being fully saturated or having a quality of 0. So that's going to define this condition here of state 5. Now from 5 to 6, we need to go from the pressure of the condenser to the pressure of the steam generator. So be careful. We know, again, the pump should be, if it's ideal and there are no losses, isentropic. So this is a constant or a straight line, vertical line. And we have to remember to go past the middle isobar and go to the highest pressure in the system, because this is how we connect back to the steam generator. and that's going to be state 6. And that maps all of these states onto this diagram correctly. And if we wanted to be even more specific, we could label each of our isobars here. That will also help us when we go to analyze this system quantitatively. So P medium, if you will, so medium, low, and high. P high is 100 bar. P medium is 25 bar. Again, we have 600 degrees C is defined as the entrance condition for the turbine at both stages, the inlet entrance temperature. And then we have 1 bar for the lowest pressure in the system, and then we condense to the fully saturated liquid. So again, that gives us the anchor. And we've used all the information that we know about these devices, the isentropic behavior of the pumps and the turbines, and the isobaric behavior of the heat exchangers. Super. Okay, so now we have these sketches, and for any time you do any analysis, you want to have a state diagram and you want to have the sketch, because that's going to be really important in reinforcing what we know about the system. So as we go to the next step, is to go through and identify the state conditions for every state on that diagram. That's what we're going to do in this analysis. It's going to take us a while, and that's one of the hardest parts about thermodynamic analysis of power plants, is that there's a lot of information and there's a lot of work for us to identify the state conditions. So it's going to take us some time, and we're going to have to use all of the process information for all of those states. So the first step is actually the easiest, which is to identify the enthalpy using the online steam tables for the states that we can. And remember, our online steam table calculator, we have the limited access edition of it, so we can only identify states for a limited region of pressures and temperatures and things like that. So we're going to use it for just a couple of the states in today's or in the next few units of discussion. But I'm going to give you some excerpts of data tables that we're going to use too. And that's a really good exercise for us to understand how to use lookup tables for the steam information. So what I want you to do first is to go online, so pause your video for a moment, and go to the online calculator and determine the enthalpy very specifically at state 1. We're going to go through step by step, so let's just start with state 1.